Okay, so it's 2 p.m., so let's start. Welcome to our web seminar. I'd like to introduce myself. First of all, my name is Nils König. I'm working for the Fraunhofer Institute for Production Technology. And I'm also serving as the vice chair for the working group 5 of 5G-ACIA, which is the working group on industrial 5G in practice. So I have the pleasure to guide you to today's webinar. And some housekeeping rules, first of all. So we will have at the end of this web seminar, we will have the chance to answer your questions. So you can ask your questions throughout the whole web seminar in the Q&A window. And at the end of this web seminar, we will try to answer as many questions as possible by the speakers. And if other questions remain open, we will try to answer them anyway. So by placing that maybe as a Q&A on the website, but the easiest way to ask questions is actually to become a member. And so there's the link given here on the slide, or you can also always contact the email info@5gacia.org. And another thing is that the web seminar will be recorded, and you will be able to access this recording after this web seminar. And all participants are muted by default except the speakers and me, the moderator. And in case you are experiencing any technical problems, please use the chat window or simply write an email to the same info at 5gacia.org. And in this web seminar, we will also launch a couple of polls to collect your input and your role and where you're coming from. So please participate in these polls. It's very easy, and submit the your result in the form, and you will be able to see the results of the polls in a live manner. So this web seminar is about the testbeds. So the testbed initiatives of 5G-ACIA. What is it about? So 5G-ACIA has a testbed initiative, which is about doing more experimental stuff. So getting 5G-ACIA in practice. That means validating solutions, 5G solutions, 5G systems, doing performance testing, and also, actually do the showcasing about the practicalities of 5G-ACIA, of 5G, not 5G-ACIA. So today we will have the presentation of two 5G-ACIA testbeds. So first testbed is 5G performance evolution for material handling and manufacturing, so which is addressing the application of 5G in material handling and logistics, basically. The second presentation of today is called 5G Zero Touch Production, and it's integrating the operation of mobile and stationary robots and entities to different frequency ranges of the 5G spectrum and edge computing. And this will be presented by Aalborg University. And the first presentation for today will be done by IFAC and DEMAC, so the two testbed partners who contributed to this testbed. So, but as I mentioned, the live polls, which you will be experiencing through the whole web seminar. So let's get started. And there's two warm-up questions for you. The first question is, which stakeholder group do you belong to? So you should be seeing a pop-up screen, and you have multiple options. information and communication technology, operational technology, academia, end users, and others. So please participate and send your role in this poll. And then you will be able to see the results live, how they are coming in. So there's still some answers coming in. So we have 25 answers from 36 participants. Okay, so 27. Okay, so we have many participants from OT. So OT is 29% and also ICT is 29% now. And then a couple of academia and also end users. So thank you for that. We have another question. So now that it worked and you got familiar with this kind of live poll. So the second one is, which region do you come from? So you have actually different continents: Africa, Asia, Australia, or Europe, North America, South America. So I already have an assumption which would be top number one. Okay, so not surprisingly, many participants from Europe. Perhaps that's also owed to the time zone we are right now. It's not comfortable for the two other halves of the globe. Okay, so we have most participants coming from Europe, and then number two is Asia with 17%. Okay, so that was the warm-up. You will be having other live polls later. Now it's a pleasure for me to hand over to my two colleagues. So Niels, having the same first name like me, and he's from Niels Kannefeld from DEMAG, and also we have Lisa Underberg from IFAG. So please, the stage is yours.
Yeah, thank you very much, Niels. So yeah, thank you for having us. And yeah, I'll now start with the presentation of our testbed. So yeah, at first, I want to give you a quick introduction to our testbed, where we are evaluating the performance evolution of 5G networks in the context of material handling in manufacturing. And then I will talk a little bit about our facilities and the use case we're working on. And then I will hand over to Lisa, and she'll talk about the measurements we conducted, the results, and also some recommendations for end users, deployers, and testing. So first, to give an introduction to the place where our testbed is, it's at our facilities at DEMAG. DEMAG has over 200 years of history in cranes and material handling. We founded 1918 in Wetter in Northern Westphalia, and we're part of the Kone Cranes Group since 2018. And we are offering different modular cranes, as well as light lifting equipment. You see the product portfolio down on the screen, as well as hoists and also drive components. I'm working in a research department here, which is called the Research and Business Factory in Germany. We're also located here in Wetter. Currently, we have 9 team members. The department was created in 2018, and we're focusing on the participation in government-funded and non-funded research projects, as well as in business-driven projects. And there, we're developing the next generation of cranes and also building different demonstrators and proof of concepts, as well as minimum viable products for our research. And we're also participating in associations and alliances, as here in the 5G-ACIA. And another big part of our work is working with students and with who are writing their bachelor and master theses at our department. So we're also training new specialists. Talking about the facilities, here you can have a short view of our research factory. We also have some office space. You can see on the right side of the factory, and there are several material handling equipment cranes, for example, installed. And we also have a 5G standalone network from Nokia, which is currently on release 15. Yeah, then in 2021 we started this testbed here at the research factory, and there we want to test the 5G technology in an industrial environment with special regards to our material handling applications and in terms of intralogistics. So here we're evaluating the performance of the 5G network by measuring. That's the first part. And we also demonstrate the use cases we want to use with the 5G network. And we do all of this together with our 4 members. So also we're working with Nokia, with Roden Schwarz and IFAC. Then our use case we want to evaluate here is that we implemented innovative assist functions in our cranes, which are semi-automatic. We will later see a demonstration of them. And therefore we're using different devices like you see on the left image in the building here, and we have an AGV, also a high lift truck, and we're also using the overhead cranes that you can see in the image. And these devices and machines are communicating with each other, and they also transfer control commands and safety functions. And because of these, we have several requirements to the communication system. For example, low latency, which is roughly in the area of 20 milliseconds or lower. And we also need high availability of our network. And the concrete benefit of these assist functions are that the worker is supported in many ways. First of all, it is possible to control the cranes via repetitive routines, and therefore we are reducing non-value adding activities like walking to get the radio control, and we also enhance safety as the operator can, it is easier for the operator to control the crane without having more option to see the environment. And now I will show you a quick video where we demonstrate the functions, and please follow along.
Hello and welcome to our research and business factory here in Wetter. Today we want to show you our 5G-ACIA testbed, and we want to demonstrate the use cases and the innovative assist functions that we implemented in our cranes.
The assist functions are controlled via a smartphone app. After opening the app, the operator first needs to authenticate himself by scanning a QR code. When the authentication process is finished, a drop-down screen appears. On this screen, the crane, the AGV, and the operator's position are displayed. To identify the positions, they are using ultra-wide band tags placed in the west and on the machines. Before this function can be used, the crane needs to be reserved. To reserve the crane, the operator taps on the desired crane and reserves it via a dedicated path. When the operator selects the trolley, 4 buttons appear on the bottom of the screen. These buttons are used to trigger the different assist functions. By triggering the Come To Me function, the operator tells the crane to move to his position. The blue spotlight indicates that an assist function is in operation. The crane then automatically moves towards the operator without any need of a radio control. Another assist function is the follow function. When this function is active, the selected trolley follows the path of the operator. A slight delay is implemented to prevent sudden movements of the crane and enhance safety. During this process, functional data is periodically exchanged by using using OPC over our 5G network. A simple function is the follow machine function. When this function is used, the crane follows a machine which is traveling through the factory. In the show scenario, the crane follows an AGV. The AGV uses a SLAM algorithm for orientation in the shop floor. The positional data is extracted and transferred to the crane via the 5G network. It is also possible to use multiple cranes and trolleys together at the same time. When activating this operational mode, the operator selects the master trolley, which specifies the position used during the process. If the so-called tandem mode is active, the safety-related CAN data, which needs to be exchanged between the cranes, is also transferred via the 5G network. In this use case, ultra-reliable low latency is needed to ensure functionality and safety.
Okay, yeah. First of all, sorry for the issues with lagging. I hope at the end you still got the idea of our use case. We will also provide the video that you can watch it again afterwards. I'm very sorry for that. I think yeah, I had some GPU issues, whatever, having the video on and also my camera. Yeah, but basically, I think you got the idea that we have data, safety relevant data, and also communication data that is transferred for the control of our cranes. And now I'm happy to hand over to Lisa, and she will now explain how we evaluate the performance of our 5G network regarding our shown use case here.
Yeah, thank you very much, Niels. You made a very good summary. In the end, Niels presented basically the first part of the testbed, which was to demonstrate the use cases that are relevant to control the cranes and to have the smart assist functions. And the second part was on measuring, and that's where IFAC and Rohde & Schwarz come into play, the two partners. And I'd like to take you on a quick trip to some example results. So first of all, we used a Nokia solution, as Nokia is also a testbed member, the digital automation cloud. On the left-hand side, you see a figure that you might already know from one or the other Nokia slide. And on the right-hand side, you can see what is important for understanding the results. That's the parameterization. We were using 5G-ACIA release 15 version in band N78 with a bandwidth, and that's a difference of most other deployments. As far as we know, we use a bandwidth of 20 megahertz only. The TDD pattern was 3 uplinks, 7 downlinks, so balanced towards downlink traffic, and a MIMO configuration of 4x4 in the downlink and 2x2 in the uplink. First, we not only conducted one standalone measurement campaign, but multiple measurement campaigns. We started out with an LTE implementation that was installed in the research factory and then moved to 5G-ACIA. For today's presentation, we selected 5G-ACIA results, and not only of default parameters, but also with adapted parameters, as the default parameters are targeted to balance energy consumption and performance. And as you have seen from the use cases, we have specific requirements with respect to the reliability and the low latency. So we adapted several aspects in the 5G network with the help of Nokia, and then redid measurements. And we will see in the following some results for the adapted 5G-ACIA network from Rohde & Schwarz. And then we will see some results comparing the parameter adaptation, the impact of the parameter adaptation from IFAC. So next up will be a quick overview on the measurements that were conducted by Rohde & Schwarz in our testbed. There were basically 2 measurement types, one passive and one active. the passive measurements were conducted using a network scanner and software for evaluating, and the active measurements were conducted using connected devices, which you can also see in the figure below, where you see what was measured in the active measurements, basically a round trip time from the measurement device via the base station to the core, to an application connected to the core, and back to the device. First, the passive coverage to get an overall impression on what the coverage was in the research factory. And basically, we can summarize that the results were very good compared to public networks within the area of interest. On the right-hand side, you can see two figures that show a top view of the research factory. In the upper figure, there are 3 positions marked. At these 3 positions, in addition to the walk test, stationary tests were performed for position 1, 2, and 3. And on the slide after that, I mean, I'm not going into details on the numbers. Please feel free to ask questions in the chat or in the Q&A box if you have any. For position 3, we selected here, oh, I have to put it the other way around, sorry. We selected position 3 to show example results, as the performance of the round trip time was nearly identical at all 3 shown positions. So position 3 is on the right hand, to be seen on the right hand side, where you can see for 5 different traffic patterns, low, medium, high, long, and industry for 0. The packet loss rate, which was during the measurements 0, so no packets were lost, and that's also something that Rohde and Schatz experienced in other measurement campaigns as well in non-public networks. The round trip time median increases with increased data rate, which is not as surprising probably, and also the packet delay variation also increased along with the data traffic. Below, on the bottom of the page, you can see very brief snapshot of about 1.5 seconds for the traffic pattern high, where you can see the variations in the round trip time. So the red line marks the median or the mean, I'm not sure by now, which is around 23 milliseconds round trip, 23 milliseconds round trip. And you can see that there are some variations. Sometimes the packets are a bit faster and sometimes it takes a bit longer. And that's something that we could reproduce in the measurements that were performed by IFAC. We used other measurement equipments, basically something that was developed at IFAC. And if you're interested on learning more about the tool, I'd like to direct you to our webpage. But in short, we connected our multifaces, as we call them, as the measurement devices have multiple interfaces, to the network, similar to what Rohde and Schatz did, but we have on one side the industrial router that the multiface connects to, and then we have some software, which we call FTT Manager, that is in charge of configuration control and result storage, and also result visualization. And what we are able to do here is not to only measure a round trip time, but to measure, for example, only downlink, so from top to bottom, or only uplink from bottom to top. And a third example that we'd like to show in the end is also from one UE to a second UE. So UE1 to core and core to second UE. I'd like to highlight once again, we're looking at now only the uplink as opposed to up and downlink measured by Rohde and Schatz. And we will now compare the results of the default parameters, the 5G network with the default parameters, with 5G with adapted parameters. But first, let's take a look at the default parameter transmission time. It took mostly always less than 20 milliseconds to go from the UE to the core network side. You see a histogram, on the right-hand side, some outliers. Please be aware the scale of the y-axis is logarithmic, which means the majority of packets were faster than 13.9 milliseconds. To be precise, 95% of the messages were faster than 13.9 milliseconds. This is how to interpret the diagram. So now when we go back to see the requirements in the use cases, we see that maybe in the uplink 20 milliseconds or sometimes more than 20 milliseconds is too long, which is going back to the 5G parameterization with Nokia. We adapted some of the parameters as said towards more performance, especially in the uplink. And what we see with the adapted parameters is that now the P95 interval is down to 8.4 milliseconds with no outliers larger than even 13 milliseconds. So that was, from the use cases perspective, a huge improvement by only tuning a couple of parameters. The challenge, of course, is to know which parameters to adapt, right? So with the help of Nokia, we were able to have an interaction on increasing or improving the uplink timing behavior. On the next slide, we can see that on the downlink, the impact on the downlink, and you see here again a histogram, transmission time, and the number of messages. Not to go into too much details, we adapted parameters that affect the uplink, which means that in the downlink, basically, the behavior we observed was the same. And you can see that here by comparing these two graphs. What we also did was an overnight test with about 10 hours in total. And here you see results from UE1 to UE2. The transmission times were low, mainly low, but we had observed some outliers, and we observed the outliers with the default parameter set as well. Here, the transmission times were much longer. Maybe let's go take a step back to look at the axis. The x-axis is the message number, which corresponds basically to a time. So time axis, and then the measured transmission time is on the y-axis, and you can see that there are some outliers only in the interval of 10 hours. The parameter adaptation did not help to remove these outliers, and this is a perfect example of how the testbed is going to help the deployer, the end user, and also the necessity of testing, because now we are investigating where these outliers are coming from to further enhance the suitability of the network for our use cases that we want to use in the DEMARC research factory, which is a good handover to our conclusion, because we conclude that we have three important parts, and that these three parts are need to interwork together. So the testing, in the testing, we learned that to understand the root cause of a performance issue, like these outliers, it not only is enough to look at the physical layer, because on the physical layer, as we've seen from the Roda and Schwarz results, everything was basically fine. But from the applications layers perspective, we measured these outliers. What we also learned is that these outliers were different for different devices, which is why we would recommend to test the configurations that match the target application as precisely as possible, meaning use the same devices that you are going to use in your very system. Of course, that does not always work because the measurement systems are different to what the end user is going to use. So we have to be interacting from the testing side with the deployer side and still learn more about how to adapt the network. For the deployer, we learned it was helpful to build up expertise in the vertical we're looking at, to see the site, to see how the 5G network will be used in the production, and finally to enhance also by the interaction with the testing, to enhance the understanding of the radio frequency propagations conditions in the plant where the 5G network is deployed. And finally, we have the end user as the interacting or as the, to repeat the word, the end user of the network. So it helped to understand the network, to learn what use cases can be supported to what extent, and to also learn that knowing your own application is also key, because the deployer has to know what the actual requirements are to fine-tune the network, and the testing needs to know what the use case is in the end to adapt testing towards the use case. Very brief, our joint recommendation is to work in a tight cooperation. What we learned here in our testbed that really helps, and that it's a good time, any time, to start testing your own network or learning about your own network for your specific use case and your business needs. So as we are in a tight cooperation, I'd like to thank you all on behalf of the testbed team for your attention, and we will now go to the second talk before moving to question and answers. Thank you.
So thank you, Niels. Thank you, Lisa. So as mentioned here on the slide, so I'd like to invite you all to ask your questions either in the Q&A module in Teams or in the chat. And we will answer as many questions as possible after the two presentations. Now I welcome the second presenters. So we have Ignacio Rodriguez Larrat. He's from University of Oviedo. He was with Aalborg University before, and we have two colleagues from Aalborg, Fatima and Sebastian from Aalborg University, and Sebastian is also connected live from the testbed site. And so the stage is yours.
Thank you very much for the introduction, Niels. So good afternoon, everyone. My name is Ignacio Rodriguez, as Niels just introduced. I will be speaking briefly a little bit about our 5G-ACIA testbed. I will make, let's say, a theoretical introduction or just provide some highlights, and then actually Sebastian and Fatima will make the live demo from the Aalborg University lab in Denmark. So first of all, I would like to introduce a little bit this testbed, which is a collaboration between OT ICT members in academia. So we have Aalborg University in Denmark, we have my university here in Spain, and we also have Nokia and Festo as industrial partners of this testbed. The main goal of our testbed, let's say the vision that we have, is to enable a safe and efficient production environment where everything is integrated, everything is automated, and in principle there are no humans, right? So we are looking that everything is done by robots. In order to do that, of course, we need to integrate and have an ecosystem that is able to operate reliably over wireless technologies. So what we are doing to integrate and build our industrial ecosystem is actually to use a 5G network. And yeah, we have the different expertise of the different partners. In the different areas, right? We have the OT, that is Festo, with production lines, PLCs, all kind of robotic equipment that you can imagine. We have Nokia providing the network connectivity. And then in this case, the ones that we are acting as integrators, OT, IT integrators, are actually the universities here. So we have developed the know-how into how to do this, let's say, in a structured manner. And we have been able, let's say, to speak to both ends, to find a common language and common understanding of both the OT and IT, so that we are able to build something like this. So first of all, I would like to launch a question to all of you, and sense a little bit for your companies how important it is to collaborate with universities. Is something that is important for you or not? So let's see if the questions are coming. 7, 8, 10, 11, 12, 13, 14. Okay, so right now we have around 20 replies, and we can see that, yeah, 65% you believe is important, 22% very important, and it's interesting that 4% they don't really know, but at least nobody's saying that it's not important, right? So it's good that you're giving some values to universities. So thank you very much for that reply. So we will continue, and I will introduce the environment where we are building this. So yeah, it's a university testbed, let's say, but we are building it in a small factory. So the small factory where we are building the zero-touch production testbed is actually industrial research labs where we have two halls. One that is dedicated to industrial automation, where we have small robots, robotic arms, autonomous mobile robots, welding chambers. And then we have another one with bigger machinery and storage area. So as you can see, it looks like a real factory. Why we are doing this? Because every time that we are, let's say, doing some research or showcasing to industry, it is important that the industrial partners understand what we are doing and that what we are doing is useful for them, right? So at the beginning of our testbed, we were, or our period doing industrial research, we were just showing slides to industrial partners, and they were not really engaging with us until we show them, like, you can remove these cables in your production line using 5G if you want, right? So that's why it's important to have a lab like this to showcase these research solutions that are directly applicable to industry. The AAU 5G Smart Production Lab is in Denmark, and as Niels mentioned, I moved to Spain, so my goal is to try to build something very similar here in Spain, and I'm currently in the way towards achieving something like this. I have to say that as a university, we know this is a 5G forum, but we are totally technology neutral. So we are, let's say, always trying to find the wireless technology that is most appropriate for a specific use case, right? In the case of the testbed that we are showing today, it will be, of course, be 5G. So a little bit about the network, the 5G network in the lab. Actually, Sebastian later will probably provide you with more details. But we have a 5G private network, so with a core that is on site. We support frequency range 1 and frequency range 2. This is one of the keys of our testbed, because I will explain later that depending on the quality of service that we want to achieve with the different use cases or applications, we choose one or the other band. And I think it's interesting that we are also supporting multiple cores. So apart from the private standalone core that we have in the lab, we have a non-standalone dedicated connections towards a public operator. Why we are doing that? Because we believe that for industrial partners, it might be also an opportunity to run some of the use cases over a public network with some conditions and help from the operators, of course. What are the key testbed elements or the technology highlights of our testbed? So as I mentioned, we want to build a fully automated and integrated setup of robotics. And the main scope for this is, of course, factory automation and intralogistics. The key elements that we are going to see here is a stationary production line that it was provided by Festo. So here we have, of course, PLCs, we have manufacturing execution system. So everything as you will have it in a real factory, right? Of course, by default, the network that is managing this production line is made of cables and switches. So it's an Ethernet network. We also have some mobile components. We have some mobile robots that I will introduce in the coming slide. Is what we call the zero-touch production robotic manipulators. I will come to this later. Of course, we have the IT part where we have the reliable and high-capacity 5G network. And here we want to explore cloudification. So we have an edge cloud that is directly connected to the 5G network. And the vision is that we can take some of the intelligence, some of the computer from the end devices or from the robotics and place it in the cloud. By doing this, let's say we can centralize all the intelligence in our production scenario, and this will help us coordinate and integrate the industrial ecosystem. IT/OT integration, I briefly explained right now. So we have two fronts where we are making an action here. So first of all, we need to provide connectivity to the robots. That's the 5G robot integration. And then once we have established the connectivity to the 5G network, then we can make some optimization depending on the control flows that we are operating. There are other multiple aspects that we are researching that are part of this testbed, but I will not discuss them here. But we are also dealing with IoT, industrial IoT protocols like MQTT or OPC UA. So once we have all our scenario fully cloudified and operating over 5G, we can play with some of the main protocols that are used in industry, just to understand what is the impact that they have on top of the regular communication. And recently we have launched a research line about absolute time synchronization of robotic elements. So we're using 5G to provide absolute time to robotics so that they can schedule different operations and coordinate themselves. And at this point, I want to launch a second question to you. and it's whether you are familiar with the concept of autonomous mobile robotic manipulators. And by this, I refer to an AMR platform that is equipped with a robotic manipulator on top. Okay, more or less half and half. Most of you didn't actually, so I think that's an interesting finding. Now 50-50. I think we can close the poll. Yes, so 50-50. And I'm going to introduce them formally a little bit this robotic manipulator. So normally in industry, we have either, let's say, AMRs or AGVs or some kind of mobile robots that are moving throughout the factory to bring products from one place to the other. But we also have the robotic manipulators that typically they are in static positions, they are in work cells or production lines, but they are not moving, right? So what we are aiming to achieve is to create a robotic element that can actually provide a higher degree of freedom in our production. So now what we are doing is to make a mobile robotic manipulator. So we have an AMR platform that is equipped with a robotic manipulation. So if we take a look, let's say, to these trends that we have in Industry 4.0 of moving towards a more flexible and reconfigurable production, where we take out the linear production and we go more for the centralized kind of swarm production with different cells distributed across the floor, we will need to transport the products from one part of the production to the other. And then these elements will be very important. In order to operate these elements that they are moving and they need reliable and high capacity communication, of course, we need 5G. And we have demonstrated already that 5G is better than Wi-Fi, than industrial Wi-Fi, let's say, for this kind of mobility situations. Actually, I'm providing a couple of references there if someone wants to take a look to this. But basically, apart from the 5G, what I mentioned is that we can use the 5G connectivity to steer the different quality of service of the different applications, right? So if we take a look at an element like the mobile robotic manipulator, we have different control loops. The platform, the mobile platform, has a control loop that has very small packets that they are very frequent and they need to be very reliable, right? In order to operate that, we are using FR1 that normally provides a better and more homogeneous coverage along our factory hall. But then, in the moment that our robotic platform will arrive to a specific position and we need to interact with the static machinery and the robotic manipulator will start to operate, then we are switching our control scheme to frequency range 2. And why we are doing that? Because the operations of the robotic manipulator, they are actually steered by video. So we are sending the video from the robotic manipulator to the edge cloud, then it gets processed, and then it will tell the robotic arm what we need to do. The video is very high demanding in terms of capacity, and that's why we are using frequency range 2. If we take a look to the entire architecture of the testbed, it's something like this, right? So we have the manipulators that they are connected to FR1 and FR2 for the different purposes that I just explained. And we also have the stationary production line where the PLCs, they are also connected to frequency range 1. And in the end, as you can see in the schema that I'm showing you on this slide, we have the edge cloud. So what we are calling the Aalborg University Factory and Process Automation Cloud, where we have all the control of the testbed. So let's say we are taking all the intelligence from the robotic elements, placing in the cloud, and they are able to interoperate between them. So we can, let's say, orchestrate all the control of the industrial ecosystem directly in the cloud, and then just transfer simple commands to the robotic elements to operate. We have been doing a number of performance evaluation results, a little bit similar to what Lisa was introducing to us before, but here we have set the focus on the specific robotic control loop actions. So we have some KPIs for the control loop. So, for example, the most important or the most novel results that we have here, they are for the frequency range 2 for the control loop of the robotic manipulator. That's the top part here. So when we are sending video from the robot arm to the cloud, it takes around 10 milliseconds because we are sending very large packets of video over frequency range 2. Then the video detection that happens in the cloud, that is some local service that we have here or either in a secondary basement, it takes around 300 milliseconds, and we have let's say, a detection algorithms with an accuracy of 100%. So it's really well trained for the products that are being manufactured in the testbed. Fatima will explain very carefully later details about the production line and the use case itself. Then, once we have analyzed the video detection and the robotic arms understand whether we have to pick up a product, we are signaling back over frequency range 2, which it takes around 5 milliseconds. And then finally, let's say the time that the internal controller of the robot towards the manipulator arm is instantaneous. After that, once we are telling the robot you need to pick up the product here, it takes around 12.1 seconds. What we have been playing also a little bit is, since the video images that we are having here, they are very similar, the compression rate can be quite large actually. So if we compress the video, we can achieve 100% scalability factor, which is a lot. That means that if a regular video transmission takes around 220 megabytes, if we divide it by 100, then the video flow is only 2 megabits per second. So we can, in principle, schedule 100 manipulators of the frequency range 2 in this case. What's the problem when we are compressing and decompressing? That we have some extra latency in the loop. So we will be adding around 160 to 100 milliseconds extra in the overall control loop, and this will have an impact on our production. But it's small, right? So we just have to wait a little bit more milliseconds, but we can scale the use case to 100 robots. And then I want also to give some highlights on the edge cloud control of the mobile platform and the production line, which has control loops that they operate in 7 milliseconds approximately. And this is round trip. So let's say PLC sending information to edge cloud and edge cloud replying, and takes around 7 milliseconds. So I want to summarize a little bit this initial introduction by recalling that we have showcased an integrated production environment where we are exploiting the capabilities of a reliable and high-capacity 5G network with FR1 and FR2 support and edge cloud technology to build this integrated demo, where we have a main element that is the 5G zero-touch production manipulator. That is a key element for the future of a smart production. If we take a look or make a couple of calculations with the numbers that I have been telling, by introducing 5G, we have a 0.7% degradation in the overall cycle time as compared to a use case where we will be running everything in the over a cable. But this means having a mobile entity that is connected with a cable to an edge cloud, right? So this is not a possibility, or at least it's something that is not optimal at all, right? So very small degradation. And later what I'm showing is that we can apply compression to increase by a factor of 100 the scalability of the use case. And I just want to highlight that only the baseline functionality and coordination has been implemented, and there is a full potential, let's say, to run further optimization and extensions of the work. And now I think we will switch to Sebastian and Fatima from the AU 5G Smart Production Lab. Hopefully the demo will work, and in any case, there is available already a video with the demo that you can always watch at any time. So thank you very much for your attention, and let's go with Sebastian and Fatima.
All right. Can you hear me? I guess you can.
Yes.
Just 1 second. Okay. I'll hand it over to Fatima. Hello, my name is Sebastian. I'm a PhD student here at Aalborg University, and my main focus is the application of 5G and how we can apply it to mobile robots. And I'm going to talk a little bit about the network that Ignacio has already introduced. So first of all, if we take a look up in the ceiling, that's where we have what we call these communication islands. And we have a lot of different wireless technologies. But let's focus on, first of all, the FR1 private 5G network that we are operating. So this is, we have 3 of these islands that provides coverage for the whole lab. And then we have configured our 5G FR1 network as a single frequency network in order to optimize for handover performance, so we can get completely seamless coverage even when a mobile robot is moving throughout our lab and then handing over between the different access points, essentially. Our 5G network, it operates in 100 megahertz bandwidth, and then the frequency is 3.7 gigahertz. And we are, of course, operating towards a completely private in-house core operated, well, we operate it ourselves, but we also purchase services from NDAC. Additionally, we have, of course, for the high capacity communication, we have the millimeter wave setup. It's basically focused around this manufacturing environment, which is where we will typically need the high throughput. This is operating in millimeter wave, of course, and it is 26 gigahertz spectrum we're talking about here. Oh, now I forget the exact numbers, but we have at least 400 megahertz of spectrum available here, spread over multiple carriers, and then you can aggregate multiple of them in order to get high throughput. And we can measure in the neighborhood of 3 gigabits per second in this scenario. Then, of course, all of the control, as Ignacio mentioned, it's happening in our edge cloud. And then we have all of this infrastructure that you can see behind me. But then we also have a basement full of servers where we have our smart production edge cloud, as we call it. That consists of 12 servers, and between them we have just shy of 2 terabytes of memory to work with, and just shy of 800 CPU cores that then we can slice and dice and distribute to whatever use case that we want. But otherwise, of course, we also do many other things here in the lab than just 5G. We also have industrial Siemens Wi-Fi. We have ultra-wideband positioning systems and many other activities. And as Ignacio also mentioned, we are hardware agnostic. So we test out different technologies and see what works best for whatever use case. And then we can mix technologies based on their strengths and weaknesses. And with that, I think that was a quick introduction to the network. And then I will hand it over to Fatima. And you'll just have to excuse us for a moment as we swab around.
Hello, everyone. I'm Fatima. I work as a student helper here at Aalborg University, working on this project. So today we are showcasing a fully integrated production environment where we have stationary elements and mobile elements, and we coordinated them using 5G technology. So the first element of this testbed is the production line, and it's called Testbeds Factory production line. Here we can see different modules of the production line, and it has different elements, conveyor and stopper button that is used for releasing the pallets. And here we have different products. Some of the products can be target phones, like in our case, black phones, and some of the phones are unfinalized, and some of the phones are not target phones. For example, in this case, blue phone, and these are on a pallet and waiting for to be processed. The other important element of our testbed is called 5G Zero Touch Production Mobile Manipulator. Here we can see, and it has different elements. So the MIA platform, which is the mobile robot, and the Franca Amica Panda manipulator, and a camera, the Intel RealSense camera mounted on the Franca, and also the 5G modem here in the robot to be used for communication. And now we will go back to production model. These products here need to be processed, and the production line will call the zero-touch production module, mobile robot. Now, as you can see, the mobile robot starts moving toward the production module, and we wait. And all of the operations, as the other colleagues mentioned, is done for 5G and Israel. Now the mobile robot is trying to dock near the production line. And now it will go to a checking position to check out the different products here on the conveyor belt. So, as I mentioned, these products are rejected because they are not a target phone, and the other one was unfinalized. But these are picked up by the robotic arm to do this execution. So the black finalized phones are the products. And here we can see also the visualization of this section. So the detection is also done in the edge guard. And now the robot will move away because it's done with the processing, and it will take the product to another part of the factory. And now the demo is finished. We have shown the possibility of using 5G for integrated automation, and the research is in progress. So I will hand it over to Ignacio to wrap up. Thank you.
Thank you, Fatima. And I think we have two Niels. So.
Okay, so thank you, Ignacio, Fatima, and Sebastian for the presentation and the demos. So I wish we would have some additional time, but time is scarce. So there were a couple of questions in the chat, and I've seen that Lisa has already answered some of them. So then nevertheless, I think we have one or two questions that we can still answer, hopefully. So there was one question from Hervé Bonville from Mitsubishi Electric, what QoS parameters are used? So guaranteed bitrate, non-guaranteed bitrate, QoS class, what kind of adaptation was made to the base station scheduler? Are you able to answer this question, Lisa?
So we would need to go back to the one slide. That's the information that we have. For example, there were two major changes. One was to disable the sleep times. And the discontinuous reception was disabled. So the UEs received or listened continuously, and we increased the number of opportunities to send uplink traffic. If you are interested, please get in touch bilaterally, or we can talk about the exact parameter. Sorry, there was a bit.
Okay, so you have written your email address in the chat, and of course all the slides or the video will be shared, so you will be able to see all the contact details. So then there were some very specific questions regarding the measurements with the ROMES package, and you have answered that as well. Then there's one question, I think that relates to Ignacio and the team of Aalborg regarding edge cloud and a private network with an industry. How does federated edge infrastructure foster collaboration and address interoperability challenges between different mobile network operators? And the realm of edge computing, in particular in the context of enhancing service quality for mobile robotic operations. Do you think any research on this topic exists?
I don't think there is that much research on this because typically that's not seen, let's say, as an academic research, right? It's more an industrial application case, I would say. About multiple network operators within a private network scenario, I don't think that's going to happen, right? So normally you have a private network that belongs to a single operator, but if to rely, let's say, on multiple network operators, normally what you do is not a fully private setup, I think. So normally you can operate and slice over the public network. And I think in that case, yeah, you can have a multi-operator setup. But that's the way I see right now. But I have to say that 5G is flexible to support many possibilities. And then about exploiting, let's say, the edge infrastructure in common. So depending on to who belongs the infrastructure, I would say, in the level of collaboration and licensing there is between the different operators. But one of the things that we are exploring, or that one of our partners that is Nokia is exploring, is this small, so we are integrating all the control in the cloud, right? Right now we are using our own server that is directly connected to the core. But in principle, they could onboard the application directly in the core. So they will minimize even further the latency. So they can use the extra computing resources they have in the core for the after doing all the routing of the UEs and so on to make some processing in the edge. And yeah, this is possible to. So it's a huge panorama of possibilities, I would say.
Yeah. So thank you, Ignacio. For me, the question of federated or not federated depends on who is actually owning the cloud-based control systems, right? So may it be the robot operator or the mobile network operator or the user. So that's, I think, is an interesting discussion. But unfortunately, we're out of time. So I'd like to a little bit show the final slide. So we are having a next round at April 11th from 2 to 3 p.m. CEST. So that's then summertime already. And again, two different 5G-ACIA endorsed testbed will be presented. One on Open Run, which is of course very timely, and very much in the interest of many stakeholders. How Open Run actually integrates into campus networks and industrial applications. And then there's one focusing purely on millimeter wave for industrial applications. And you can register for this webinar already now, like the way you did it for today. So you follow the typical channels on 5G-ACIA or the LinkedIn channel, and you won't miss the registration for the third web seminar on the 5G-ACIA and those testbeds. So I'd like to thank you very much for the for participating today, and see you next time.
Thank you very much.
Thank you.
Thank you.